The plan today is to delve a little bit more into the world of power. Give you some time to work, and we'll likely look at kinetic energy. Oh, I said we were going to do the power lab part, right? Yes. So, come dressed or prepared to run up the stairs. Don't wear high heels or a suit or what have you. Wear clothes, flip-flops maybe. Wear something that you can run up the stairs in. We'll do that tomorrow. And we'll determine your horsepower. Okay, let's begin. As always, you can choose to write down as much or as little as you wish. Okay? These are actual notes, but again, write down as much as you choose or wish to. John, I think you should repeat down. You don't mind. Now, for me, we talked more about work yesterday, right? So I posted it, and I think it's there. We didn't do any work. Just check. Okay, so power is simply the rate of doing work. If you're taking calculus, anyone taking advanced math? Hey, have you done you've done differentiation?
Very last unit.
You haven't done differentiation yet? What have you been doing?
We're doing matrices right now.
Oh, matrices.
Limits, derivatives.
Yeah, derivatives. Oh, have you done derivatives?
Yeah.
Okay, well that's what the derivative is, the rate at which the function changes, right? So if you were to look at this from a calculus standpoint, if you've got a work function,
Or squared.
then power would be the derivative of work. Have you done integrals yet? Integration. Have you done integration? No? Okay, well, it's just the reverse. It's kind of like the area under the graph kind of thing. It'll all make sense to you when you see it. Okay, so power is simply the rate of doing work. You could say it's also the rate at which energy is transferred from one object to another, or from one form to another. Okay, so like mechanical energy converted to gravitational energy. Chemical battery energy converted to mechanical or heat energy or something like that. Transfer of work, transfer of energy. All good? Yeah? Oops, I guess that might be too fast. From a mathematical standpoint, it's the amount of work done per unit of time. And in a formula standpoint, just from the definition, it's not even really a derivation because it's defined as, anytime you've got per unit, you're dividing by, right? So it's simply, and you've seen this already, P equals W over T. It's one of the easier formulas you're going to see in grade 12 physics. Power equals work over time. How fast do you get it done? How powerful are you? Well, we'll find out tomorrow. I actually had a top 10 at one time, but I sort of stopped maintaining it.
Who was number one?
It was surprising. It was a rather large boy. And the reason that he was the top was because he was so large and he was actually surprisingly quick for his size. And because he was as quick as some of the smaller people, he had a greater power rate. I was surprised too at the difference in male to females. I thought that the females would be as close to, generally because they're smaller and probably just as fast, but it seemed like the boys just cared more about the competition and tried harder. And it just, I don't know why, it just seemed like that, right? And I don't, that came across as sexist. I didn't mean it to be like that, but I was surprised at the difference, right? So maybe this is the year girls will outdo the boys. No? And it doesn't matter, you don't have to be faster than them, you just got to be more faster for your size, that's all. I was surprised at the difference, Brady. We're really getting into some, I really shouldn't have brought this up, eh?
I think cervix.
I apologize, ladies. Well, we'll see tomorrow. Everyone,
I'm putting my money.
you're putting your money on him?
I'm putting my money on a risky team.
What are the units of power? Do you remember?
Joules.
Well,
Calories.
power is work over time. Watts? Watts, yeah. Work is measured in joules Time is measured in seconds, so technically the unit of power is the joule per second, which is known as, or is defined as, a watt. And it's the same watt when you've got a 100-watt light bulb. You know what I'm talking about? You've been hanging out with me too long. When they talk about the new dams that Manitoba Hydro is going to build and how many watts of power they're going to generate, that's what they're talking about. There you go. James Watt was the guy that's named after. Wouldn't you like to have a unit named after you? Did I have this conversation with you guys already?
It was during the
I'd like, that's my lifetime goal, to have a unit named after me.
Are you doing research to somehow make this work?
No, it's never going to happen.
Maybe it'll just happen one day.
Maybe.
Hey, we'll get it trending on Twitter.
Yeah, that's a good idea.
Just like,
Eh?
last name too long, you wouldn't have a good time.
My name is too long. Oh yeah, 47 DeRoches.
That's not good.
Yeah. You're right, most of the units are, well, 2 syllables, right? Watt. Newton. Joule. It's a good thing the name, the guy, whatever. Okay, so this is going to tie right into what we do tomorrow. How much power does a 50-kilogram girl develop? Develop is the word that is used, the verb, excuse me, while running up a 2-meter high flight of stairs in 0.75 seconds. So this is exactly what you're going to do tomorrow, right? We're going to weigh ourselves. We're going to use the Newton scale. You don't even have to multiply by 9.8. What power does a 50-kilogram girl develop while running up a 2-meter high flight of stairs in 0.75 seconds? Note that she does work against the pull of gravity. She's pushing down on the stairs pushing up on her. She's working against gravity, right? So it's her weight force that has to be applied. For the same amount, I guess I should say. Yes, I was supposed to be recording right now. Thank you, Zach. I'll just pause now, waiting for those people watching it on video to write this down. Too late. The textbook uses a slightly different formula that I want to introduce to you as well. So I'm doing a little bit of formula derivation here as well. It's not that hard. It's pretty one of the easier ones. P equals W over T. We just saw that. Work is F times D. So I've got power equals F D over T. But what is D over T equal to? Right from like grade 10, you know that D over T is velocity. So I'm going to replace that D over T with a V. And what am I going to end up with?
P equals FV. Maybe.
Oh, we divide something.
Power equals force times velocity. Has Mr. Ray told you that classic joke about the calculus professor convention?
No, I want to hear.
Where they were told at the end of the night, make sure you don't drink and drive?
Oh, yeah.
Did I tell you that one? Yeah. That's a good one. I won't tell it to you again. Maybe I won't.
But was there actually a story to it, or that's it?
No, that's, well, you can make up as much story as you want, but that's the punchline. There are some textbook questions that you can do if you wish. Those ones will take advantage of that formula there, so just be aware, I guess. How about we do a little clicker quiz? Yeah. It'll be question number 1. Yay, everyone got it right. I wish my grade 11, I haven't yet to get my grade 11s get all right. Okay, so which student does the most work? It is the same amount. How come? Same. Oh yeah, because it's the same amount of work, right? Same amount of energy transfer. It doesn't matter who does it faster. The work is the same, right? MGD. But the next question is, which one is the most powerful? Why is it B, Ben? Because he does it in 10 seconds, whereas Will takes a whole minute. So it is B, Ben. Good job. Jack and Jill ran up the hill. Jack is twice as massive as Jill. We got a 50-50 split here, but the correct answer is A. Who does the most work? It is, the answer is Jack, because he's bigger. So at the top, he's got twice as much potential energy. right? It doesn't matter the time. Again, who did the most work? So it is Jack simply because of his size, right? He's at the same height. He's twice as massive. He does twice as much work. But which one is more powerful? And the correct answer is C. They are the same because she's half the weight, but does it twice as fast. So it works out, right? So Jill is, or no, I should say they're both the same power. That's what it says, isn't it? Yeah.
You're right.
Okay. A tired squirrel of mass approximately 1 kilogram does push-ups by applying a force to elevate its center of mass by 5 centimeters in order to do a mere 0.5 joules of work. If the tired squirrel does all this work in 2 seconds, determine its power. Power is work over time, so 0.5 joules over 2 seconds. 0.25 watts, I think, right? Yes, 0.25. When doing chin-ups, the physics student lifts her 42 kilogram body distance of 0.25 meters in 2 seconds. What is the power delivered by the student's biceps to 1 decimal place? Well, power is work over time. The work is FD, and in this case here it is weight force. So that's mgd divided by time. So 42 kilograms times 9.8, the distance is 0.25 meters. This all happens in 2 seconds, and you should get, what's the answer? 51.5? 51.5 watts, right? Not sure what these people got. I could go and look. Yeah? Easy? Okay? Most people got it. Here the answer is 36 with a whole bunch of zeros. How many zeros, right? It's 1,000. A kilowatt hour is 1,000 watt hours. And an hour is 60 minutes times 60 seconds, which is 3,600 seconds. So a watt hour, or 1,000 watt hour, is 1,000 times 3,600, or 3,600, and then 1,000. That would be a watt seconds, which are joules. A watt second is a joule. So when you buy a kilowatt hour of electricity, you are getting, what is that? 3.6 million joules. Anyone know what a kilowatt hour of electricity costs these days? I can tell you exactly because I teach it in grade 9 science. It's relatively cheap. Want to take a guess?
20.
20 what? 20 bucks?
Cents.
7.831 cents per kilowatt hour. Electricity is pretty cheap. You get 3.6 million joules of energy.
What can I do with that?
Yeah, what can you power with?
Well, go back there. Go back there. Look at the power rating on that fan there, Jason. I think it's about 45 watts. Am I right?
Yeah.
Okay. So power is 45 watts. So if you ran it for an hour, it would be 45 times 60 seconds times 60. Someone do that for me?
162,000.
162,000.
Yeah.
So that would be 162 kilowatt hours if you ran it for an hour. So 162 times 7 cents cost you a couple dollars, I guess,
For how long?
for an hour.
Also, we figured out yesterday at work, after reading one of the granola bars, that the conversion rate is like 4.1.
Between-
Calories times 4.1 will give you joules.
Really? Wow. You guys do some pretty weird stuff at work.
Is that right?
I don't know the conversion rate, but
Well, something like that.
I'll check it out. I've got it.
I think it's thought you closed.
Yeah? Was it a slow day at the coop?
I was facing, I was looking at the protein.
Oh, yeah?
I was looking to see if it was outdated.
How'd you do it?
Just did it.
Really?
We just, because it gave you.
We'll give you joules and give you calories.
Yeah. Did a bit of quick division.
It was
Awesome.
more of a, yeah, that was about 4.
4.1.
4.1.
Okay, well, let's do it right now. I want to know.
I think we're
What is it? Joules to calories, right? Oh, 1 joule is, you want to go the other way?
Oh, just divide that by 1 by that number. It's easy.
That's just what kind of what I came up with.
4.18.
There you go. Nerd alert. Well done, I'm proud of you. Yeah. You're at about, on a scale of 1 to 10, you're about I'd say about a 6 Bennett's.
Hey, let's do it.
There's my unit. The nerd unit. That's why I'm going to have a unit named after me? Degree of nerdness. Oh. An escalator used to move 20 passengers every minute from the first floor to the second. 5.2 meters above the first floor. The average passenger's mass is 54.9, and we've got 20 of them, right? So mass is going to be 20 times 54.9. Someone help me out. $1,098, right? We're looking for power. Power is work divided by time. In this case, it's the weight force times the distance divided by time. So it's going to be mass times gravity. So 1098 times 9.8. The distance traveled is 5.2 meters. And it has to happen in this every minute, right? So divided by 60. So that number times 9.8 times 5.2 divided by 60. 932.6 watts. Am I right? Is that what you got? Oh, nearest whole number. Oh. Okay, if you can do like this question, I wouldn't worry about this one. If you can do that one and this one, you guys are doing fine with power. We're good.